Hello, everybody. I'm Vladimir Ivanov, still working on Hotspot JVM JIT compilers at Oracle. And today I'm here to tell you about Vector API yet again, but in a more like broader setup. So I'll try to cover past and present of Vector API, and but the goal of the talk is more like forward-looking. I'll share some feedback we heard from Vector API users, and based on that, I'll try to come up with a forward-looking vision where we may move at some point. So it's primarily, I'll lay the foundation talking about Vector API, its current status and how we ended up there, what kind of benefits we see and what kind of limitations people report. And then based on that, point out opportunities for growth. There was a recurring theme how to grow a language. Similar reasoning applies to platform as well. We don't want to just pile features on after feature in JVM level as well. We want synergies of different features to get us more benefits when they're applied together rather than individually. And I'll try a thought experiment with a hypothetical hardware intrinsics API, and let's see where we end with that. So the primary motivation for Vector API was to expose to the users a way to do data parallel operations on data in cross-platform manner and in like being predictable at the same time. One of the issues Emmanuel pointed out is that auto-vectorization is brittle. That's the problem we wanted to avoid by providing some guarantees how it behaves at runtime. So there were three main goals of the project. So be maximum expressive and portable. Back in 2015, we didn't want to advertise any platform-specific stuff. Like let's expose something applicable to all possible platforms where Java is relevant. At the same time, we wanted to be performant. And by performant, I mean not just the maximum performant. We wanted to squeeze as much as possible from hardware, but at the same time, giving some predictability guarantees, like not like it breaks randomly, like depending on the phase of a moon. But if you get it working, it works, irrespective of what you do. And the graceful performance degradation, it doesn't just break, it slowly slows down depending on the mismatches you observe at runtime. Compared to, for example, just-in-time compilation, you have the optimization when you switch from compiled code to interpreter. And from a user perspective, it looks like your application runs like 30 times slower. We don't want users aren't happy about that. They want, they can accept slowdowns, but not as big as those. So a quick recap. How many people tried Vector API? How many people remember what's Vector API is all about? How the code looks like? Okay, I'm happy. That's a JVMLS, at least. So speaking of API design, there are three primary aspects of it, three mostly independent axes. So it's operation applied on some vectors. Each vector has a shape. And those operations are applied to some data. So for example, in this particular case, it's a dot product on two primitive arrays of floats. So we do a dot product, so we load vectors from which multiply, then sum the elements and accumulate and write it into accumulator. So that's one of the simplest case you can do with vector API. You're free to do as much more complicated things with it. So speaking of the evolution of the project, we started back in 2015, and the implementation went through three major phases. So we started experimenting with machine code snippets and superlengths as a backend. So API stayed mostly the same until late 2020, when there was some slight adjustments before the API was started incubating. So it started as the implementation started as machine code snippets, and the superlongs were used to represent vectors. Then we did an experiment trying Valhalla, and at that time the MVTs were the next big thing, and we did vectors on top of that. And once we started productizing, like preparing for the integration, we switched to intrinsic-baked, JVM intrinsic-backed representation for operations, and typed vectors as the representation for vectors themselves. And 2021, JDK 16, the first release where vector API was included as incubator model, and since then it was incubating. So this September, in a month, there will be a 10th sort of an anniversary if you count JDK releases. There was even a proposal to drop the number, so it's a common practice to include what the number of iterations spent, like how many releases it has been incubating. And for JDK 25, it was a 10th consecutive JDK release where vector API is incubating. So there's some people asked, why don't we drop it? But it's still there. So there's clearly, you can clearly see how many releases it has been there. And it's not just re-incubating. There is a healthy stream of changes going in. So, and that's like sort of a major improvements which affected the API. Not just like I dropped bug fixes and the smaller enhancements which affect VM. So as you can see, a lot of investments over past 5 years since the vector API became a part of release of JDK. Meanwhile, there was adoption in the community as well, even though it's incubating. People found a way to use incubating APIs in their products. So as an example, Apache Lucene found a way, a use case for vector API along as with the foreign function for FFM API. And it was back in JDK 2021 timeframe. So speaking of what have we learned since then, first of all, it's that incubation can take time, especially when some aspects are out of your control. Like for vector API, it's primarily, the primary dependency is on Valhalla. So we are waiting until the first deliverables arrive. And we were like happy to be close to VM. There's a lot of, meanwhile we're waiting for more VM support, we were able to use ad hoc knobs we introduced in the VM since we have a luxury to be close to VM. So there was an opportunity to co-evolve both JDK and VM. If vector API was just a separate library, we didn't have that opportunity. Speaking of API challenges, one of the downsides, speaking of the feedback people report on the API, they can be split in two categories. Like some people are happy, and you normally don't hear from them. Some people say like why the API is too complicated, why it's too low, so low Like, why can't you lift it and like operate on the whole arrays rather than on, like, why do you expose a packed vector representation at all? Just hide it. And there was a separate category of users who aren't happy with the abstraction we provide. Like, why can't you expose that particular instruction we care about? So for them, Vector API is way too low level. So some people want a easier to use API. Some people want more control over what's happening. And separately from that, as an example of the ease of use case, if you look at the API design, what went really well is the representation for operation and shape. It's really nice how you can abstract over the actual representation of the vector, how big it is. Switching from 128 to 512 is mostly seamless if you care about lane-wise operations. Like operations, you can substitute any shape of transformations seamlessly as well, apply like arbitrary transformations for a vector. So those parts were really good. But the data isn't that, that doesn't fit the overall design that much. As an example, if you care about performance, and Emmanuel gave an excellent overview why alignment is important. So if you care about the most performant way to code Vector API, you won't end up with a single loop. You'll start with a pre-loop to do alignment, proper alignment. Then you have a main loop. And depending on how big your vector is and how big your data, you'll end up with something which won't fit into the vector. So you'll have to post-process it. So you end up with 3 loops: pre-loop, main loop, which is a vectorized, and post-loop. It forces users to code the same logic 3 times, which is unfortunate. Why can't we do that only once? Speaking of API-wise, there is a way to code it in a same way by using masked operations, but those aren't that well optimized. So as of now, your VM isn't your best friend here. So this code will be less performant than manually specializing loops. Fortunately, there is progress on that front as well. Back in 2017, if I remember correctly, Jan Graves gave a presentation on this stage, speaking of lifting scalar code to vectors by having an AST representation. And those representations were manually coded. You had to compose them by hand. Since then, a lot changed. So there is Project Babylon now and code models. So you can use Java-C to prepare the AST representation for you, and based on that, lift the scalar code to vector code, like apply it to Vector API. In a similar way, you do that for machine learning, like having a scalar representation, you lift and then offload to GPU. Speaking of closer to hardware requests, one of the examples was like, there was an attempt to code some crypto algorithm in Java and using Vector API. And the question was, why can't we use this? There is a special instruction, VP mul DQ, on x86. And what it does, it takes lower parts of 64-bit elements, multiply them, and store 64-bit results. And the only benefits compared to the full-blown 64-bit multiplication is that it's much faster. On Intel CPUs, like 3x faster, like 5 cycles versus 15. So there is clear benefit to be able to code the algorithm with the latter. So how do you expose that particular instruction on Vector API? That was the challenge we faced. You could expose a dedicated, a special operation specifically for that, but then you would have to provide an implementation for all other platforms which don't support it. And it won't perform in the same way, performance-wise, as the original instruction, so not much benefit for others. You could try to detect some special patterns and compile those on JIT compiler side into that particular instruction. And that's what we ended up with in the end. But it doesn't scale, first of all, and it's cumbersome. So users have to use special patterns for particular instructions. That's way too much work, both on API side for users and for implementers like us. And if you operate on integers, on ints, on 32 bits, when you load them from memory, you have a packed vector of ints. And in order to apply that instruction, you have to scatter the result. You have to turn the int vector to long vector. And when you operate on maximally supported vector size, you end up with twice as many vectors in that operation. So you have to operate on lower part, on the upper. So it doesn't work. It doesn't look pretty. It's only downsides for users and implementers. So the lesson we learned there is that there is a whole class of algorithms which become viable only when there is access to particular hardware instructions. Back then, Richard Statin, who actively experimented with Vector API, coined the term snowflakes. So those are instructions which are so special. You can't unify them under like a cross-platform view of the question boils down: why can't we provide direct access to hardware instead of trying to guard users from it through some additional layers? And remember, the motto for Project Panama is to get Java closer to hardware, not the opposite. So now I plan to switch to the next topic, and that's hardware intrinsic API, and shape it as a thought experiment how such an API could look like in Java, like back in 2015 and in the modern days. I'll start with let's recap how hardware landscape looks like. Back in 2015, this was just early days of AVX 512. That was like one of the Intel has been adding vector ISA extensions for some time by then, and there was a shiny new thing, AVX 512, announced a year or so before. And John summarizes the overall impressions really well in that tweet. So we were scared. How many instructions? How irregular it is? So it was a whole new thing a whole new approach to think about parallel processing. What has changed since 2005? It's 2025. How does it look like today? It didn't get any better. So Intel has been adding new and new variants, incremental improvements for AVX 512, and at some point they changed their mind and they came up with AVX 10, which is sort of obsoletes AVX 512. So it's intended to supersede it, because in a multi-core era, it's very hard to provide a uniform view of the hardware even on a single CPU. It's common to have performance-oriented cores, efficiently-oriented cores on the same die, and even Intel switches to P and E cores in their terminology. So you can't provide the same level of functionality across those. So that's what the thing Intel struggled for some time. I didn't mention that here, but AMD jumped on the train as well. They were avoiding AVX512 for a long time, but with the Zen 4, they finally introduced support, and it was a really good one. So these days, AVX512 and not Intel specific anymore, but it has a good support across some major x86 vendors. What about other architectures? So during those 10 years, Arch64 got something new as well. So it's SVE and SVE2 these days. And finally, some time ago, you can actually try hardware with SVE supported. Some architectures disappeared, like SPARC, but the new architectures also showed up, like RISC-V. And RISC-V has a separate, a new design of vectors, like a separate way to express vectors. So it's even complicated things even more for us. So let's switch to the topic of the API. How could the API providing such functionality look like? So we care about hardware intrinsics. And the ultimate goal is to provide to users a way to call a method, and then at some point in the implementation, it ends up executing that particular instruction. So it's a low-level platform-specific API. You can think of separate interfaces for individual ISA extensions, which provides access to individual machine instructions. Each instruction is guarded by a capability check. So if you run on a hardware which doesn't support it, you have to check first whether it's supported or not before calling it. One of the interesting things is that it's not specific to vector extensions, even though those vector instructions consume the majority of instruction space these days, but you can apply it to any instructions. Ideally, we want one-to-one mapping. So a method corresponds to a single instruction, not a sequence of instructions. And the last but not least, probably the most important part, is that we want it to be performant, on par with the raw performance of that particular individual instruction. So that's like a Java version of what I've described. Something. So what are the most evident questions? Like there are plenty of questions which you can ask about that API, like how to name things, how to bind each individual entry to the instruction, what's the representation for vectors you want to rely on. But if you want to naively implement it, like it's like a big problem. So lots of manual work for each individual instruction because each individual entry point requires a lot of work if you consider it as at the same bar as the Java API. And there are tens of thousands of instructions. So it's almost impossible to justify the investments to do such kind of API. Back in 2015, we faced a similar problem when we started working on Vector API, and it was a pristine landscape. We had only JNI, unsafe, and JVM intrinsic in our hands, and we wanted to code with vector instructions. And JVM support for vector instructions was very limited. Remember, it was just a year. Intel announced AVX512, and we didn't even have hardware access to AVX512 capable machines. So what could we do there? We decided to come up with something novel and ended up with machine code snippets. So the idea was to wrap an arbitrary machine code and represent it as a method handle at runtime. So the representation was based on native method handles. We have been experimenting with FFI in Project Panama for some time by then, and we had a prototype to interact with native code. So we had we already ended up with native method handles. So machine code snippets were one step forward, and we merged native method handles with JVM intrinsics, and it turned out to be a very interesting approach. It was excellent for our exploratory. There are some engineers who worked with it back then, and I'm sure they have something to share on that. But for that use case, it was perfect exploratory development. You could pick any instructions you wanted and get it working. So it gave us enough performance we looked for. During early stages of development, it was targeted at small code snippets up to a dozen, but there was no hard limit on that. And the nice thing was that it covered all the execution modes. So it worked in interpreter, C1 and C2, and we optimized it in C2, so we get the most performance in C2. So we started with something simple. There was a factory which turned as like a raw machine code, just like a hard-coded instruction sequence and represented as a method handle. And eventually we went through the multiple optimization rounds, and there were multiple iterations, giving us more and more performance for the implementation. So the more we experimented with it, the more problems we faced when it came to performance. Like if you take the code as is, you get conflicts on registers, so the generated code, the code around those snippets gets polluted with the numerous register moves. If you ask people what's the problem with the register moves, they should be mostly free. It's not the actual performance, how expensive the actual reg-to-reg move is, but how much code they consume. So you lose the code density. So like you get individual vector instructions and a lot of unnecessary redundant instructions around that. So we came up with register allocator-aware snippets, and then we thought about why do we need to care about effects, possible effects. So we made that explicit as well. So when you when you declare a snippet, you could say whether it writes to memory, reads memory, and the C2 benefited from that. But the ultimate goal was to improve the performance. So we looked for as much performance as possible. So it's like if we look at that from those 5 criteria I chose, it significantly improves the situation compared to naive implementation we started with. So naming is free. You are free to name your method handles as you want. API size is minimal. It's just a single factory. The binding side, you have to explicitly enumerate all the instructions one by one. And beware, be careful. If you misspell something, it will crash. Most likely at a random place, unrelated to your code, so better be cautious than sorry later. As I mentioned, it covered all the execution modes, so default implementations were automatically derived, so you didn't need to do anything special about that. And the JVM support didn't care about what kind of code you wrap, so it covers everything uniformly. So 10 years later, can we do better than that? Like what has changed since then? Like Vector API is part of Panama, and Panama has been moving on. for 10 years. So since 2015, we got Java foreign, finally public, as part of public API. In last year, we have a vector API incubating. We have a jextract doing a really good job processing very complicated large header files. And we learned a lot from machine code snippets. So what can we do better? Can we come up with something better than what we did 10 years ago? Let's try to apply this story we have been building for native libraries to hardware intrinsics API and try to treat it as just a C API, just an external library we want to use from the Java program. So you end up with like native toolchains provide access to that API, and those are normally shaped as header files. Like on x86, Intel advertised intrin header. ARM has its own ARM_neon and ARM_SVE. RISC-V has its own API to access that type of API, specifically hardware intrinsics targeted at individual instructions. So jextract produces Java interfaces, and then at runtime we just code against those, and like, can we get what we want in such a way? Well, what provides implementations for those functions? Like where does the individual instruction comes from when we call into the entry point? So we extracted something from the header, but where is the backing library? Those header files, they are like a thin wrapper around built-ins. So there is no dynamic library available at runtime. You have to build it yourself. So that's one thing we can do. So jextract can be extended to produce Java interface along with the C file, and that native C source file then compiled into a library. Then the library is produced from it. And that library can contain the instructions we want. So if we look at imintrin, give that such an experiment with libintrim. And here is the table of the instruction size, how big the entry points for each individual native entry is. So as you can see, like there are quite a significant number of very small ones, like 0 and 1 instructions. Like it counts return instruction. So 1 means empty instruction, empty entry point. So it just returns. So 2 instructions, total count of instructions, means there is an instruction doing the work and then we return. And there are a set of like larger, like 3, 4, 5 instructions. So like more than 2 instructions usually means there is some argument processing happening. So we narrow the set of accepted ranges. We move register, for example. On x86, when you pass a mask value, like those which encode the K1, K7, end up in K1, K7 mask registers. Those are passed as general purpose values on GP registers and then have to be moved to the K register. So those populate the majority of those like 3 instruction entries. But there are also like much larger in size instructions. So if we care about one-to-one mapping, not everything in the header file satisfies that restrictions, and that's like a deliberate choice of API developers. So they include the much larger cases there as well. So for example, in this particular case, it's end up as like more than 50 instructions in total to compose a 512-bit vector out of 32 float 16 scalars. Another problem I spotted when playing with that is that due to some native toolchain peculiarities, it may end up as another instruction, wrong instruction, compared to what's advertised. So even though the entry point is for malix instruction, it ends up compiled with imal, and that's wrong. And there is a mismatch with the like jextract and API extracted from it. Like there are some of the entry points are defined as macros, and those have some constraints on the arguments. So if, for example, you can't pass the known constant as an immediate, so that's the limitation of the native API. And if you want to expose it through Java API, you have to find an alternative way to code it. On H64, the situation is better. There are much more compact result if you process Neon, at least. I tried with this V, but it didn't give the same. Like, I spotted way too many bugs in native compiler with it, so it didn't work that well. But speaking of Neon, there are like much denser entry points in general. So once we end up with that library, at runtime we can call into it and get what we want. Do we get what we really want? Mostly. So it improves everything except since it doesn't have JVM support, the call into the stub, which actually ends up calling into the entry point, is the best we can do right now. So performance-wise, it doesn't meet the goal. So what can we do better than that? So how can we try to optimize the code? So if we look at what kind of information JVM can extract for this particular case, we get an entry point, we see mesh encode, but we also have a header file, so we have like symbolic information, what kind of argument it accepts, what results it returns, and if we sort of analyze, try to parse the entry point and extract some additional information from it, we can get a lot of information just by looking at the individual instructions we see. So like all AVX512 instructions are coded with EVX prefix. There is opcode for operation, and if you look at the actual encoding, there are dedicated sites at the instruction where the arguments, where the actual registers are encoded. So if you look at the different encodings of like different instructions accepting different registers, they differ only at that particular place. So it's possible to patch only those and end up with the same instruction, with the same semantic, but as operating on different registers. Meanwhile, the actual operations are coded as like they occupy different bits in the encoding. First of all, it's opcode, but AVX prefix also affects how the instruction is interpreted. So if VM is able to extract that information out of native code, it can code the instructions directly when it needs to. So it automatically extracts the information from the entry point and then the code. But it has to be simple enough to be a viable option. So we have a whole a chain of possible optimization opportunities when it comes from starting with a stub call and ending up as an optimized mesh encode snippet in the end. So we can inline the stub, avoid it, do a direct call into an entry point, try to inline the entry point itself, and but don't change it at all. So if we can prove it's safe to reuse the code, we can keep all the effects and just avoid the call itself, the overhead of the call. And if VM is smarter than that, it can patch the instruction and get the... Javelin in foreign implementation, we are the first at the top. So all the native calls are calls into a stub. While with machine code snippets, we went way down to the optimized representation. So that's the gap between Javelin foreign right now and the machine code snippets when it comes to performance when operating on a very short native entry point. In practice, most of the time it doesn't matter because you call into something much bigger than that. But for the use case we are looking at right now, it matters. It matters a lot, and machine code snippets prove that. So considering VM is capable of doing that kind of tricks, we sort of alleviate the last missing piece, which is affects performance. So and that's like different grades. Like we can start simply inlining and end up with specializing the code. So what kind of missing pieces this design steps on? So we can't properly describe the API headers provide. So, and it's not specific to Imentrin. Like some of the native libraries use defines, inline functions, and those aren't covered by jextract yet. So linker doesn't support vector calling conventions. That's another limitations. GDK and JVM doesn't have a canonical representation for vectors, and that affects ability to represent vector calling conventions. And C2 is very the repertoire of optimizations JVM does for native functions is very limited right now. But that's the current state of the Panama-related functionality in 2025. So I have not too much time left. So the challenges, I went through that. So one of the limitations we already stepped on is that the code quality affects a lot. So like if native compiler doesn't produce a decent result in the library, VM is out of luck. So that's the weak spot for that. From a VM perspective, the main limitation is that is the medium which is chosen to interact with libraries, and that's the native code. So depending on the shape of the machine code, it's on one hand, it becomes harder to provide predictable performance characteristics because if something goes wrong and the native compiler doesn't produce the good result, expected result, you're out of luck. VM can't optimize it. So how to ensure the library and VM matches, their expectations match, so the code may achieve the needed performance characteristics. So the nice thing about that, it's all like for experimentation and an open question, but the nice thing is that it's amenable to exhaustive testing. So all those individual pieces can be tested separately and ensured. And at runtime, there may be an API to let code query to query whether that instruction is not only supported, but properly optimized as well. And the VM can be careful about what kind of instructions it supports, actually tries to optimize. So there may be a wide list of individual instructions under the hood on the VM level, which it trusts. But it's all about combinatorial explosion at all levels. So we start with a huge API size. When we try to avoid that, we end up with implementation challenges on VM level. It's basically the same. And we went through that with vector API. So it was like fighting with the complexity. And it's an open question whether it's an inherent or accidental complexity. We were quite successful at eliminating it. So I believe It's more about accident. It's more to be accidental, but still, like as of now, we still have a lot of complexity related to all those specializations in VM, especially in C2, where we have multiple implementations of operations of different shapes, vector operations of different shapes on VM level. Fortunately, there is some progress on that. Well, some time ago, people tried to parse header documentation. Intel publishes, that was Golang. But since then, they use it to produce the machine, the assembler implementation for their internal needs. But rather, relatively recently, Intel published a library which featured a machine-readable description of their ISA, and that can be used to actually extract the information we need in VM level. So it's not only like knowing what instructions are there, but what kind of effects. So in this particular case, like the definition describes what registers are read and what are written, even so CPU ID doesn't have all that information in encoding. So that's a sort of a fixed registers the instruction operate. And the last thing I wanted to say, like the other part of API is CPU capability checks, so those which are required. But in practice, those capability checks are just a prerequisite. It doesn't guarantee anything except the CPU accepts those instructions. So it's common to have new instructions to have poor performance when it comes to actually measuring. So for example, when AVX2 was released, the gatherers were like almost slower than doing like individual scalar operations, but they significantly improved that in the subsequent releases. But it's not always the case. So for example, if you look at long vector multiply, the one we went through earlier, on Intel, there is a 3x difference, but AMD treats both in the same way. Like they both have very good performance. And that's not specific to that particular instruction. It's common to have some instructions perform really well on some microarchitectures while others suck. So in practice, CPU dispatching turns, if you care about performance, it usually turns into an exact microarchitecture check. You look not only on the support for ISA extension, but for that particular microarchitecture, you measure it and where it performs really well. So that's it. Thank you.
A lot of examples. 2 questions. So first, have you considered using architecture descriptions from Hotspot as a source for getting all the instructions? Because anyway, all that is duplicated there. And by the way, they have the same issue with extra limitations, predicates, like guarantees for some instructions, because there are limitations, obviously, for arguments. But sometimes they may give you already closer, more detailed information closer to hotspot, like what registers could be used, etc. So some other limitations are already expressed there, and anyway, this information is being also supported there. Yeah, and second question is like about the API. How do you see the thing that you mentioned, that templated intrinsics with the different architectures? Is it really possible?
So speaking of answering the first question, which is related to why not reuse what we have in Hotspot. What we have in Hotspot, we it's hand-coded. Like we go through each individual case, and there should be a justification. It's error-prone. We learned the hard way that it's hard. So while thinking about that thing, that stuff, I wanted to avoid that particular problem. Can we have something more reliable then somebody manually going through that and producing the implementation, and then we need to test it. So like it's not that uncommon to see problems with the newly introduced instructions. So there are slides where like some higher range registers aren't coded properly because on x86 it's a lot of complex interaction between different prefixes, that kind of stuff. So I mentioned the machine code readable specifications because they have a complete coverage of the instruction set. So if we can benefit from that, it's not specific to the idea of hardware intrinsics. It can be used for JVM internal purposes. We can try to automatically generate our assembler definitions based on that. We can try and then port to them. So like it would save a lot of complexity on hotspot JVM side. Speaking of the API, it's sort of like the whole idea is to avoid specifying it as an API. So it's something very special in a sense that if you try to enumerate everything, it becomes almost intolerable, way too big for something to standardize. And as you can see, those things constantly change. So like 10 years ago, we looked at AVX512, it was a shiny new things. These days, 10 years later, it's sort of obsolete. Let's call it that way. There is AVX10, and everybody have to migrate to it eventually. So it's a relatively fast-moving area. Speaking of like API stability. So the idea, the design I tried to draw to think through was more like how to avoid all the complexities involved with that. Provide a set of primitives, both on tooling, VM, and JDK side, which can enable users to import pieces they want, not the ones we carefully chosen for them. Somebody needs an instruction, and there is a way for them to bring them into their application without going through the whole cycle of standardizing that particular piece of API. We did so that exercises with vector API. Somebody comes and say, okay, I need saturated operations support. Okay, we can consider it. Then we implement it, test it, propose it for the next reincubation, and eventually it shows up. So if somebody asks for something very specific, it's much harder to justify bringing it as part of any API. And the scope of API is huge. If somebody asks for that particular instruction, there may be very few people who actually care about that, but they care about it performing really, really fast. And that's one of the main complications to getting that the problem solved, because the API, the problem on the API side is the whole size of the API, tens of thousands of instructions which are operations which are platform specific, and on the implementation side, that should perform as if it were natively supported, like the VM knows perfectly. So with a proper set of primitives, we can leverage that and get, maybe not fully supported, but we're much closer to getting that problem addressed as part of Project Panama. That was the main, yeah. Where is it? That's it?